Okay, Neil, so we are going to start. So let me introduce our keynote speaker to everyone today. So hello, everyone. So first of all, welcome to the Codex Super special session. I'm Hongyi Li. Today, our first keynote speaker is Dr. Neil Zeghidour. Neil is co-founder and chief modeling officer of the Kyutai Research Lab. I believe many of you have heard the name of Kyutai Lab because they built Moshi, the first real-time full duplex spoken language model. I believe most of you have played with it and found it very amazing. And he was previously at Google, and when he was at Google, he also working on spoken language model. He has built lots of very well-known models, including SoundStream, AudioLM, and MusicLM. I believe all of you have heard these models. So we are very happy today. He can have time to be with us online and share with us more about speech and audio language model. So let's welcome our keynote speaker. Thank you.
Thanks for having me. Thanks for the nice introduction. So yes, today I'm going to give an overview of the work I've done with my teams at Google and at Kyutai on audio language models. And to start, before I would like to say a few words about Kyutai. So we just got a nice introduction, but maybe I could say a few words about it. It's a lab we created in Paris a year ago. And it's a non-profit research lab focused on open science, which means our entire mission is about making research, publishing papers, and open sourcing codes and models. We get generous donations from various philanthropists, and we are always recruiting, looking for good talent, working mostly on multimodal large language models. So now back to the topic of interest. The idea of audio language models was to create foundation models for generative audio. So the first motivation for the work I've done was to try to get a generic way of training audio models that could then be used for various generative tasks. For example, text to audio or audio to audio, or even unconditioned generation. So at the time, there were a lot of models for audio generation. The main ones that were very popular were generative adversarial networks. However, when we thought about the properties of such an audio foundation model, we thought the following characteristics were what we wanted. So we wanted to do generative pre-training on massive unlabeled data because that's what was easily available. To have generic pre-training loss. In particular, we really didn't want to have something that was specific to speech. We wanted to find a generic approach that could work for audio, music, speech, that could model very complex long-term dependencies while learning high-level structure and having zero-shot abilities. So when we look into the literature, what we saw it was that these kind of models were kind of rising in text, right? So it was around the time of GPT-2 and GPT-3, and we were starting to see that language models would provide such things for text. So that's where our inspiration came from. And so if we look at how we train a text-based language model, basically, you are all familiar with it, but for the sake of the demonstration, I will give a brief recap. You give it a sequence of words or a sequence of tokens, and you train it to predict the next one. So then the question is, how do we go from a text language model to an audio language model? And here, the first difficulty we faced is that audio has a much higher sampling rate than text, right? So we can have a few characters per second of speech when represented as text, while even at a low quality such as 16 kilohertz, we're going to have dozens of thousands of samples. Yet, back in 2016, there was a first early approach at applying language models for audio prediction. In particular, it was WaveNet. So in the context of WaveNet, the main idea was to have a language modeling of the waveform after quantization. So language model is a classification model. It's trying to predict the next class. So since the waveform is a continuous value, what they propose is to discretize the waveform into a finite set of values with scalar quantization, and then train an autoregressive model for next discretized waveform value prediction. Transformers did not exist at the time. So to model long context, they relied on dilated convolutions that allow to have a receptive field that grows exponentially with the number of layers. This was a groundbreaking work in text-to-speech, in particular, because for the first time, a purely waveform-based model could outperform traditional TTS systems. However, it was very slow, which means because the main issue was when you did inference, you had to produce at 16 kilohertz 16,000 values per second, which was just a ridiculously long sequence. And the second issue was that it did not learn high-level structure. So it's not in the paper, but it's on the WaveNet blog post. WaveNet is a text-to-speech system. However, the authors also showed a demonstration of how it behaves when you don't condition it on text. So they also run inference in pure audio mode without conditioning. And in that context, you get this kind of audio.
Just even. Dat wist dus. Dus laat zo uit verkeerd of je challenge. Dat is een could I Jeff over. It's over to hit to be the nota day.
Please let me know if you couldn't hear well. But basically, the idea here is that the quality is very high. It clearly sounds like natural speech. However, it's babbling. So the model was able to learn, the natural sound of a voice, but didn't learn language from scratch. So this led to an idea, which is that instead of predicting the waveform directly, what if we had kind of pseudo characters that are going to be the most similar possible to text characters, but that will represent audio? What does it mean that they will be close to text? First, they should be low frame rate, because in particular, we don't want to predict dozens of thousands of values per second. They should model the semantic information, so the high-level structure, while allowing for reconstructing high-quality audio. So ideally, we would have an encoder that takes an audio, transforms it into these pseudo characters, where we can perform next-second prediction, and then a decoder will convert these generated tokens back to audio. So I think a very seminal work in that regard was the work by the team of Emmanuel Dupoux at Facebook AI. It's called Textless NLP. And the main idea is the following. They start from a Hubert model, which is a self-supervised speech model. And it's trained with a machine language model criterion for representation learning. Originally, Hubert was proposed for pre-training for speech recognition, so for discriminative tasks. It was not meant to be used for generative tasks. What they showed is that when you have trained Hubert, what you can do is pick a layer in the middle of the architecture and project your audio into that representation space. Now you have a continuous semantic representation of your audio. Remember that we need a discrete representation because we want to train a language model. So what they do is that they train a k-means that is going to go from a discrete embedding from a continuous embedding, to a discrete representation. And then you can train a language model for next token prediction in this representation space. So the big advantages were the following. It's fully unsupervised because Hubert is unsupervised, k-means is unsupervised, and then your audio language model is unsupervised. It's very low frame rate as well, because unlike WaveNet, instead of modeling audio at 16 kilohertz, you are at 50 hertz now, which is much more reasonable. And I think the most impressive and groundbreaking result is that for the first time, a model could learn the structure of language, so grammar, lexicon, even some kind of semantics, and it could learn it without having seen any text, just by listening to speech.
In some parts of the country, where white stones in the lakes are so large that a common liquid flattened all the ground is greater than the top, and the beaches are so white.
So it's not a very interesting sentence. However, it's a sentence that is grammatically correct and carries some kind of semantics. It's kind of coherent, right? So it was really one of the most impressive work, I think, and a very early work that kind of influenced everything that came afterwards. However, it came with fundamental limitations. The first one is that the tokens were very speech specific. Hubert was trained on clean speech. It was only meant to model clean speech. Also, the decoder was speaker specific. The thing is that the Hubert tokens were too compressed to model both the linguistic content and the speaker identification and the speaker identity. So what happened is that it was the task of the decoder to reconstruct the speaker voice. So it was not trivial to have a model that could work on any voice, any kind of recording conditions, and so on and so forth. So, which means that the semantic part was solved back then, but the acoustic part, the idea of having acoustic tokens that could model all the rich information that is not linguistic, was still missing. So it's around the time where we developed SoundStream. So SoundStream was kind of the first neural codec that could compete with traditional codecs. In particular, it was generative adversarial networks with vector quantization in the middle. In particular, we introduced residual vector quantization in this paper. And this allowed to have very high quality even at low bitrate. So to give you an idea, that's the kind of quality you'll get with Opus and with SoundStream. So when we developed SoundStream, the main idea was not generative models. We developed SoundStream for real-time communication. The idea was to have a codec that could be used in a video conference like this one and allow for high quality. However, when we read the paper about textless NLP, it gave us an idea. So now we had tokens that instead of being speaker-specific and speech-specific, could be used for any kind of audio. So what if we just trained a language model to predict the next SoundStream tokens? We were very confident that it would work, and it didn't work. So in the case of speech, here is what you will get.
And for Annie, outside that, it was as though a dark cloud was conjunction, she can of the.
Sorry, so the quality is pretty high, but the speech is still babbling. So we are back to the problem of wavenet. One thing we observed, though, is that when we did continuation, the voice of the speaker was perfectly preserved. And this gave us the idea to furthermore, later on, invent zero-shot voice cloning from a few seconds. And we also observe the same thing with piano. So with piano, here you're going to hear 4 seconds of real audio and then the continuation. So this was pretty disappointing and also exciting because, so obviously it's piano, right? It's natural piano. However, there is no musical structure in it. So we had solved the kind of the quality aspect, but we lost the high-level structure from the semantic token of textless NLP. So we came up with a very simple idea, just combine both. So we introduced the naming of semantic and acoustic tokens. What we call semantic tokens were these kind of tokens that model high-level information but cannot reconstruct high-quality audio, while the acoustic tokens, coming from SoundStream, will rather model all the acoustic details. And we propose the hierarchical modeling of these tokens. So a first language model will just predict the semantic tokens based on the past. Then, the key idea of AudioLM is that the semantic tokens will serve the role of scaffolding to predict acoustic tokens. So we will use them as a prefix to predict acoustic tokens, and then we will just throw away the semantic tokens and reconstruct audio from acoustic tokens. So your question may be, okay, but what's the point of semantic tokens here? Semantic tokens, they serve kind of a guidance, a conditioning to the generation of acoustic tokens to guarantee that the high-level structure is going to be preserved. This allowed us to propose the first model for zero-shot voice cloning and continuation. The idea was the following. We would have a 3-second prompt of audio.
Some images, like some sensations.
We will transform it into semantic and acoustic tokens. Then the first stage of AudioLM will predict the future semantic tokens. And now we will have the semantic tokens, both the prompt and the generated one. Sorry, there is a mistake in the figure. And we will predict sorry, there is no mistake in the figure. And we will predict the future acoustic tokens. And that will allow us to now have the first model for speech and music continuation that will allow for keeping the high quality speaker identity and so on and so forth.
Nay, nay, lording, answered Wolf. We know not how to call you lord or lady. We have lived too long in the forest, and are now
So this was a very exciting result for us, but obviously that was not our end goal, right? Because our main motivation was to do conditioned generation, as I said in the beginning. The continuation task was kind of a debugging task for us. It was a way of developing the models, the architecture, the tokens, and so on. But when we saw how good we could do speech continuation, we decided to work also on text-to-speech. And when we saw that we could do piano continuation, we realized that we could have developed the first text-to-music system, which I will present later. Now, let's start with text-to-speech. In that context, an actual task that is much more interesting than just speech continuation is to have a text and generate the corresponding audio like this one.
Oh, what a grand thing to happen on a raw day.
So the idea of how we address text-to-speech is the following. If we look at what we showed in AudioLM without text, so a pure audio model that has never seen text, it takes semantic tokens and predict acoustic tokens. So in a way, what we could do is just take text as input and produce acoustic tokens, right? Because the semantic tokens carry the linguistic information, we could just replace them with text. This was done by Valley, which is kind of this idea of conditioning a model with text converted to phoneme, and then have a language model that is going to produce acoustic tokens directly that can then be mapped back to audio. So a limitation of this kind of approach is that if we look at the training data, so AudioLM was trained on audio-only data, both for music or for speech, it was audio-only. But now you need to have pairs of transcript and speech, right? So you need transcribed audio. So the problem is that if you want to handle multiple speakers and new conditions, you need annotated pairs in that domains. This is a limitation because labeled data is rare in most languages, and you don't want the diversity of generated data to be dependent on the diversity of labeled data. To give you a concrete example, let's say I train my text-to-speech system only on male voices. If I wanted now to work with female voices, I will need to collect transcribed data from female voices. So it's a big limitation. So we saw an opportunity here because unannotated speech is widely available. And so we proposed an approach that could not only require a minimal amount of transcribed data. In particular, we were able to train a TTS system with only 15 minutes of data, of parallel data, sorry. But also what we showed is that we completely decoupled the diversity from the label data, which means that we are able to only have label data in one speaker and have the model generate any voice. The main idea was the following. Now we have, again, a hierarchical model, but it's a bit different than AudioLM. The first stage goes from text to semantic tokens. And the second stage goes from semantic tokens to acoustic tokens. And here what we observe is an asymmetry in the nature of the data that you need. In particular, the first stage requires parallel data because since you go from text to semantic tokens, it means that you need to have parallel text and audio. However, since the second part is only from semantic to acoustic tokens, it's totally unsupervised. So you can train it on audio-only data with very high volumes. The main question here then is, what is exactly modeled by semantic tokens with respect to acoustic tokens? To probe this kind of information, a simple experiment is the following. You take a ground truth audio, you compute ground truth semantic tokens, and you generate various acoustic tokens, right? So you always keep the same semantic, and you just repeat temperature sampling for the acoustic tokens. So here is what you see.
This transient spring and lighting up are beautiful. A glamour.
So that's the ground truth, and here adds various generation of acoustic tokens.
This transient spring and lighting up are beautiful, a glamour beguiling our senses.
This transient spring and lighting up are beautiful, a glamour.
So it's pretty clear what happens here is that every time we change the acoustic tokens, the voice changes, the recording condition changes, and so on. However, the text remains the same. So that's how we observe that semantic tokens will model the linguistic content, and the acoustic tokens will model everything else. So this gave us this key observation. In particular, since the speaker identity is modeled by the acoustic tokens, there is no problem to train the first stage on single speaker data, because even if our parallel data has a single speaker, it's the second stage that is going to bring the model its ability to speak in various voices. So As long as the second stage is multi-speaker, the first stage can be single speaker. And this gave us this kind of ability.
Spare TTS with 24 hours of parallel data.
Spare TTS with 12 hours of parallel data.
Spare TTS with 2 hours of parallel data.
Spare TTS with 30 minutes of parallel data.
Spare TTS with 15 minutes of parallel data.
So what we observe is that, and for all the metrics, I rather would have you refer to the paper for the sake of time and rather go across the many contributions. But not only the linguistic content is preserved even with very small parallel data. What is very interesting here is that the quality, the audio quality and the speaker diversity is completely independent from the amount of parallel data. So we are able to completely decouple both aspects. Sorry. Then, similarly to what we did with AudioLM and then was done by Valley, we could do voice prompting from a few seconds. Now, the main difference instead is that we could just have a text to control what is said. So the input to the model will be a text and an audio prompt.
To see the signs of adolescence that made.
And we could generate this text with the voice.
And yesterday, things went on just as usual.
So in terms of quality, what was interesting is that despite having 15 minutes of parallel data instead of 60,000 hours, we are able to have speaker similarity almost on par with Valley and an audio quality that was just to be much better. To be fair, there were a lot of confounding factors because we were not using the same codec and so on. However, it was to show that we were able to reduce the amount of parallel data to very small amounts, which could be very useful for low resource languages. Then again, what I said in the beginning and something that is very important to me is from the beginning, both when we developed SoundStream and AudioLM, our priority was to find generic principles that could work for any audio. We really didn't want to have something that is specific to speech. In particular, traditional text-to-speech with neural networks will be very speech-specific. You will have a phoneme duration model and a prosody model and so on and so forth. If you have this kind of prior knowledge, it helps for your task, but it doesn't transfer to other tasks. That's why we kept AudioLM and SoundStream as generic as possible. There is pretty much nothing that is specific to speech. To illustrate that, we applied the same idea from text-to-speech to text-to-music. So in that context, instead of having something you want to synthesize, you have a prompt and you want to generate the corresponding audio. So again, now the model is almost exactly the same, but we need new type of data. So instead of having transcribed speech, we need pairs of caption and music. However, it was very clear from the beginning that we could not train a text-to-music system with 15 minutes of parallel data because the mapping from text to semantic tokens in speech was kind of an easy mapping because both were very close in terms of the information they contain. However, a high-level caption like 19's house music is kind of far to the corresponding music in terms of representation. So this mapping is much more complex to learn, much more ambiguous, so it requires more data. This kind of data is very difficult to collect and obtain. It was the case back then in 2023. It's still the case today. In particular, there is no existing database that will be of a large volume, like we would have with LibriLite or where you would have with Lion for images. So it was a bit challenging to find this. And what we did is that we relied on multimodal embeddings that were developed at Google called MuLan. My understanding is that it will be close to something like CLAP that is used widely rather than MuLan. And the main idea of this kind of model is the following. The idea is that you learn a representation space where if I give an audio, music audio, and the corresponding text that describes this audio, this will be close in the embedding space. And if they don't represent the same information, they should be far in the embedding space. So it's a multimodal embedding space where you can map a song both as its audio version or its textual description, and both representations should be ideally very close in the representation space. And the nice thing about this is that once you have trained these multimodal embeddings, you can train your text-to-music system without text. Because let's say I want to train my model to predict audio from Berlin 19th house. So I don't have text and audio music. So what I do is that I just take my unlabeled music, I project it into a MuLan embeddings, and it becomes a conditioning to my language model. So during training, I don't need text. You can see there is no text in this diagram. I can only train on audio. But then at inference, we want the user to be able to provide a textual description. So now, instead of computing the conditioning to the language model with audio, we pass a text description through MuLan. And since MuLan represents both audio and text with similar embeddings, it just works to train on audio only and then run inference in kind of an out-of-domain way where you give text as input instead of audio. So I'm going to play a few samples, but every time I do this presentation, it's less and less impressive because now you have Suno and Udio that are extremely impressive models. Please remember that back then, except for Refusion, I think there was pretty much nothing. So this was kind of the first work that could do very complex and rich description and turn them into music. So to show how much the AudioLM framework was a generic framework that could be used for a lot of things, we also did another fun task that is called reverse karaoke, where you go from a voice to an instrumental. So in that context, you pass it an a cappella. So it takes time to load. And you generate the corresponding instrumental. So going very, because I'm running a bit out of time, just to go quickly, here the main idea is that now you need parallel a cappella and instrumental. It's very simple. You take a dataset of music, you apply a source separator like Demux, and then you separate the a cappella from the instrumental, and you train the model to predict the instrumental from the a cappella, and now you have your reverse karaoke music model. One thing that was very important to us was to bring human in the loop in this context. In particular, automatic evaluation of music generation is limited. For people who have worked on this topic, it's one of the most frustrating aspects is that you cannot really trust the automatic metrics, so you spend a lot of time listening to audio. In particular, subjectivity is something that is very hard to model, yet it's very important in evaluation. So we will need ideally to integrate humans in the loop, like was done, like is done for text language models. So what we did is that we released MusicLM to the world through a web app, and we made a specific design choice when we made the UI, is that we decided to allow the user to give a trophy for, so every time they would pass a prompt, it would generate 2 audio, and the user could pick their favorite one. They could not give 2 trophies. They could give 1 trophy if there is 1 audio that they preferred. And that would allow us to get a preference, because what we learned from our colleagues working on reinforcement learning is that it's much easier to exploit preference rather than absolute gradings, like giving a rating from 1 to 5, let's say. We collected about 300,000 preferences, and we're able to do RLHF for music generation for the first time. And the resulting models is what is currently used in all the APIs of Google for music, like MusicFX DJ and so on and so forth. So all of this is using this kind of feedback loop. So I stole your figure because I presented mostly the work I did with my team, but obviously it contributed to a much wider effort across industry. I am proud to think that what we did has inspired a lot of work. For example, the work of my friends at Facebook working on Encodec, MusicGen, also work across industry. And because beyond research, NotebookLM relies on AudioLM. Suno, in its first version, also relied on AudioLM. So it had kind of it became one of the main approach to audio generation, along with diffusion. So basically now you have these two families of model, either audio language models or diffusion models. And I'm very happy to have been able to contribute to the development of audio language models. So a year ago now, I want to say a few words about what I've been doing at Kyutai. I left Google and with the goal of doing a new project that will be a groundbreaking project in audio. And we decided to work on a real-time conversation for a specific reason. Even though we had, with AudioLM, we were able to do basically any kind of audio generation task, text to music, text to audio, speech enhancement, speech separation, text to speech. So we did pretty much everything we could. There was one task where we had made absolutely no progress, and nobody seemed to have made progress, which was to have a real-time full duplex conversation. So what will be new about that is that if you look, unlike standard voice AIs, if you look at the standard pipeline to how you do voice AI, is the following. So you have a voice activity detection that is going to decide when to record your query. Let's say I want to ask what is the capital city of France. Then when the voice activity detection detects that I'm done with my question, is going to, an automatic speech recognition model is going to transcribe my text into my speech into text. Then a large language model is going to produce an answer, and the text-to-speech system is going to produce a spoken answer like it's Paris. There are two main limitations with that. The first one is that it's pretty slow, right? So you get typically between 3 to 5 seconds of latency. And the second issue is that you lose all the non-linguistic information, like the emotion and so on and so forth. So because you go through this bottleneck of text. So let's say now you would like to make an assistant that trains you to do job interviews. It's a bit challenging because when you train for a job interview, you can do it right now, let's say with ChatGPT, but a real job interview can be very stressful. The people can try to challenge you. So, they are not going to patiently wait 5 seconds every time to answer you. The conversation can go pretty fast, and it can also evaluate your emotional behavior and so on and so forth. So if you wanted to create an assistant to train for job interviews, you could not use existing voice AIs. Another thing is that now I guess you are all familiar with the advanced voice mode of ChatGPT. So it's a model that reduces the latency to pretty much, a few hundred of milliseconds, virtually zero, let's say. However, it's still limited by the way it represents a conversation. Any voice conversation model is half duplex. So it's like a talkie-walkie, in the sense that it considers that a conversation is a clean segmentation between a user turn, then an AI turn, then a user turn, and so on and so forth. However, a real human conversation looks like what you see below. You have interruptions, you have back channeling. So sometimes you are going to say, but the person should keep talking. It can go very fast, can be very chaotic. It's more like being on the phone with a family member. So statistically, if you are on the phone with a family member, up to 20% of your speech is going to be overlap. So most of 20% of the spoken time will have two people speaking at the same time. So this completely breaks the assumption of the half duplex. And one use case for this, for example, is let's say you would like to play video games with a lot of AI in the TeamSpeak. The situation here in World of Warcraft is very chaotic. A lot of things happen. It's very, it's a very complex environment. So you need your model to be very comfortable with the ambiguity of a complex audio with overlapping speech and so on and so forth. And to give you an idea of what it could look like, here is a video of me trying to play MMORPG with Moshi.
Hello, what's up?
Hi Moshi, let's pretend we are wizards and we are fighting a giant dragon that is coming right to us, okay?
Okay, I'll be the wizard and you be the fighter.
Okay.
How do we start?
Okay, so as a wizard, what kind of spell can you cast to protect us?
Well, I have a spell called Fireball that can create a ball of fire and throw it at our enemy.
Okay, can you cast it right now against the dragon? It's coming closer to us.
Sure, I'll cast the spell.
Okay, on my side, I will start attacking it with my bow, okay?
Sounds good.
So now, so for the sake of time, I will not play the entire conversation, but basically, it's it gives you an idea of how we could do that. So when we go from AudioLM to Moshi, one problem is that we have much stronger requirements than continuation because we need to be real time and streaming. So we cannot model semantic and acoustic tokens separately. the model needs to be much smarter than AudioLM. So it needs to rely on an LLM backbone. And we need to have an explicit modeling of both user and AI speech so that the model is going to understand what is their speech and what is the user speech. I'm running a bit out of time, so I'll be very quickly, but the main idea is that we use a hierarchical model inspired from UniAudio and RQ Transformer, where instead of having this flattened model of tokens, our large model predicts a continuous embedding that becomes the input to a much smaller transformer that predicts the tokens for a single step. So now we have a model that is going to scale to much longer sequences and that can operate in real time. The second thing is that if we want to go from continuation to dialogue, it's very easy to do half duplex. You have your sequence of tokens, and you're just going to concatenate the tokens of the user and the tokens of the AI. It works, but it cannot model overlap. So the simple idea is that we have two streams of tokens now as input instead of one. We always model one stream for the tokens of the user and one stream for the tokens of the system, so that both can speak at the same time, both can be silent at the same time, and so on and so forth. I will skip on the a fun demo unless I think I have only a few minutes left. But so then there was a question of how we create the data to train this model. And so we created synthetic data by hiring a voice artist, and we wrote with our text LLM a lot of scripts for her, and it allowed us to train a TTS
This
system.
time I'm not chatting, but rather being controlled by text. I can express more than 70 emotions and speaking styles.
Like whispering.
Or maybe I could sing a song.
I can sound terrified.
So we created this emotional TTS system, and we used it to generate unlimited amounts, basically, of synthetic data that look like this.
Hello, what's going on? Do you watch a drama series? If so, which one? Yeah, I do. There are so many good ones.
Again, for the sake of time, and I'd rather have you read the paper, but basically it was the first multi-stream TTS as well that can create full duplex synthetic speech that is used then to train Moshi. So to summarize, because I'm a bit late, Moshi is the first full duplex voice AI ever. So we start with an online demo on Moshi.chat. Then we release weights and code, and a 60-page research paper on archive. It can run locally on your MacBook with these two simple commands. And as a conclusion, I will say that audio language models are very dear to my heart because we showed that they are strong foundation models, and they are also natural candidates for multimodality because what you can do is you can tokenize images, text, audio, and then have a single model predicting all these modalities with a unified architecture, which is basically our approach at Kyutai, the approach at Gemini, and so on and so forth. What is next? And that will be my final word. One thing I have not been able to make progress on so far, and I'm really looking forward to happen, is emergence in terms of zero-shot abilities. Now, what we see in text language models, they are able to do any kind of task with only few-shot prompting or even sometimes zero-shot prompting. It will be amazing to show that a speech model that was trained in unsupervised fashion can do impersonation, can do voice transformation, and so on and so forth in the zero-shot manner. Thanks a lot for your attention, and if there is time, I'm happy to take a few questions. Thank you.
Okay, let's still take probably one or two questions. So any question from the audience? Okay, there. Okay, we have a question behind.
Hi, Neil. Thanks for your great work. And I observed in your AudioLM, you tried the self-supervised features with two vector BERT. But in Mosh, I observed you used WaveLM. So is there any difference between the two or any other self-supervised representations?
So Wake-to-Wake BERT is not open source, so I could use it when I was at Google. Since then, I think there was an open source application by Meta. But basically, the main idea is that we could have used Wave2Egbert or WaveLM. I don't think it would have made much differences. One thing that was very important for Moshi is that we needed the semantic token to be causal, because the Wave2Egbert is bidirectional, so it cannot work in a streaming fashion. You cannot use it in a real-time conversation because you cannot encode it until you have some context in the future. So that's why we did a distillation from WaveLM into causal tokens that can be computed in a streaming fashion. One thing that is interesting is that we also tried distilling Whisper activations, and it didn't work at all, despite Whisper being state-of-the-art for ESR. So there is probably something to explore there.
Okay, thank you.
Oh, any quick question? Okay, the last one, the one at the third row. Okay. Yeah, I know you have more questions, but we have limited of time. Sorry.
Thank you, Neil, for your presentation. I have a question regarding Moshi. So the last stage training of Moshi is trained on 2,000 hours of data, right? From Fisher. And I think, it seems like the text input is different from what is used for pre-training the helium temporal transformer. So do you think, is there any mismatch, or like how much does the pre-training help for Moshi?
Okay, so good question. So the last stage is not Fisher. Fisher is used at some point to because it's the only existing full duplex data we had. However, we used Fisher mostly to train a multi-stream text-to-speech system, and then the final step is purely synthetic data. So it's a fake conversation between Moshi and a user. It's around 100,000 hours of data in this fashion. Obviously, it really changes from the distribution of text that is used to train the LLM backbone. What you can see in our model is that Moshi, it's much worse on question answering than its LLM backbone. And I think one theory for that is that there is much more high-quality content in text data than in speech. So in text, you have Stack Overflow, Stack Exchange, Wikipedia. You have a lot of sources of high density of information, very informative. In audio, it's much more difficult because if you wanted to synthesize the entire Wikipedia, it would already represent a huge volume. So that's why we want to make progress on how we merge the knowledge of the text model along with the speaking abilities.
I see. Thank you.
Thank you. Okay, I think due to time limitation, we have to stop at here. Let's thank Neil again to give us a wonderful and insightful talk. Thank you very much. Thank you.
Thanks a lot for having me. Very happy to be here.